Welcome back to ECE 442-542. A lot of activity today. Apparently they realize homework number 1 is due today, and you have until midnight, actually 11:59, to submit that on the D2L Dropbox. If you are taking this class online, the proctor agreement form needs to be filled out and submitted to its own Dropbox. Homework number 2 is due in a week. Question? The PDF version is the preferred. The question was, how do you like how do you want these submitted? A PDF version is preferred in terms of one file, so the grader can open up your homework assignment, and that would be it. So if you've handed in separate files, this one you'll just get a 0 on, if that's okay. It should be fine. I'll just, in the future, if you can compress it, or not compress it, but put it all into one file, that just helps the grader, I believe, instead of the grader having to open up individual files. But if it's in different formats, it's okay too, but I think the preferred format would be a PDF file for the grader, and then everything is more consistent. Our exam number 1, is a week from Wednesday. And there is practice material on D2L on the content page. What you might do, just to see if you have a grasp of what we've covered, you might try to list down what we have covered this semester. There is a list of topics. You can check that. And there's obviously a lot of practice exams that you can look at. I'm assuming we might have a review session next Monday after this class. So if you're really into a marathon session, we'll be here starting at 7 on a week from Monday. But if you're not into it, I will try to record. And if it turns out that we can't have access to this room, maybe I'll go lock myself in a room and just do it by myself and then make it available to you. That will be really fun and exciting for me. So hopefully we can gain access to this room. I need to put in that request. If you have particular topics or questions you would like to see reviewed during the review session, I've created a quiz on D2L. It's not really a quiz, but it's a way for you to type in your question that you might like to see covered on during the review for exam number 1. Questions on that? And you'll find that underneath the quiz tab. Hopefully you'll be able to find that. And I also tried to provide a link within the content of the exam number 1 material, and hopefully if you click on that, that will take you to the quiz also. We'll see how that works. Today what I want to do is the following. Review our unit step waveform in the continuous time or analog setting and in the digital setting, and we'll go over where this convergent geometric series comes from and how that now leads us to a region of convergence and why we might be interested in the region of convergence, because that will be important throughout the remaining class time that we have together, not just tonight, but the entire semester, is understanding the region of convergence and how that relates to these time domain waveforms or these signals. We'll then derive the Ztransform, or then we'll review the exponential waveform for the analog case and show how that leads naturally into a different or a discrete version of an exponential waveform. We'll derive the Ztransform of the exponential waveform for the discrete time case. We'll then look at a exponentially damped cosine waveform and how we can find its Z-transform. That may be as far as we get today, but if we have time, we'll get into Z-transform properties. Just like the Laplace transform has certain properties, so does the Z-transform. and we'll look at the frequency response of h of z. Now, if you were into fitness, maybe the earlier classes were better for our fitness because then we had to walk an infinite j omega axis. Now for frequency response in the z domain, we just have to walk a finite amount on the unit circle. So we'll talk about what the frequency response looks like in the z-plane. Now it's just a walk around the unit circle from 1 to -1, for example. And that will be how we would then evaluate our system's response due to sinusoidal inputs. And we'll hopefully become more comfortable with that as we go into the material throughout the class. As promised, here's our review, or the start of that. For a unit step, for the analog setting, we have our time domain and frequency domain. The time domain is this constant value for all non-negative time from t equals 0 to infinity. And the pole zero diagram, if we look at the diagram associated with the poles and zeros of the Laplace transform of the unit step, that simply is 1 over s, which leads us to one pole at the origin in the complex s-plane. That's the unit step for the continuous time setting. In the discrete time case, now we have this picture. Now we have 1 at discrete intervals of time. And here I'm not identifying what that time period is between each sample, but that's our sampling period, capital T. Whatever that is, now we're seeing 1 at 0, at 1. It's 0 for for negative time and 1 for non-negative time. The Z-transform of little u of n is now this capital U of z. That's the frequency domain version of our unit step. And that's this infinite sum when u is non-zero. And it's non-zero over non-negative indices, little n. U of n equals 1 for non-negative values of the argument, little n. And last time, or if you just plug in those particular values and expand out that sum, you will see that capital U of z is now 1 plus z to the -1 plus z to the -2 plus z to the -3, and it just keeps going and going and going. It never quits. But we derived last time in a hurry, so we'll sort of pick back up on that tonight or today, this closed form expression. We can actually show that that infinite sum actually does collapse down into a closed form expression, which could be written two different ways. 1 over 1 minus z to the -1, or in terms of positive exponents on z, z over z minus 1. And if we look at the zeros and poles of capital U of z, we see that a value of z equals 0 gives us a 0. So we have a 0 at the origin in the z-plane. Now this is a complex plane, but it's the z-plane. Contrasted with the other complex plane, which was the s-plane, which is what we work in when we have continuous time waveforms. Now that we have discrete time waveforms, we're in the z-plane. And we also have a pole at the value of z that causes the denominator to vanish, or when z is equal to 1. Our region of convergence is actually all of this shaded area outside of this unit disk. And what I want to do now is go over or provide a little background behind where did that closed form expression come from, and what is this region of convergence, this ROC. We're into rocks. This is a geology class if you didn't know. No, we won't cover those kind of rocks, but this material just rocks, right? Never mind. ROC. Bad jokes, fine. First, geometric series. So now you can listen to this tonight and see what happened during that few second interval that we weren't actually on. But we now have this example, which is a geometric series where we are looking at 1/2 raised to the n, just to get a feel for what's happening in general when we start doing these Z-transforms. We want to know why can we simply say that this infinitely long sum actually collapses down to just produce a result of 2, or this 1/1 minus 1/2. Well, if you look at each of these terms and look at the two, or let's say look at two terms together, if you take the ratio of subsequent terms, you will see that they differ by a ratio of 1/2. And because that ratio is less than 1 in magnitude, this will converge. If you wanted to, you could get fancy and start drawing squares of area 1, then area 1/2, then area 1/4, and you'll see that you actually start to tile in an area of 2 by adding up this long infinite sum of areas. That's another way of visualizing what's happening when you sum 1 plus 1/2 plus 1/4, etc. But in this case, it's a geometric series, which means that each new term is a factor away from the previous term, and that factor is the common ratio of 1/2. Now, contrast that with a harmonic series. And here we're not going to be in the School of Music. This is not a musical harmonic series. This is actually, I'm sorry you can't see this on the video, but we now have a music stand in the front of the classroom, and it has the School of Music, very appropriate. I had them bring in this prop just for today's class. Harmonic series in math. Now we have 1/1 plus 1/2 plus 1/3. This one looks similar to this previous one, except it's a little different. A little different. But what can we do here? This one actually is bigger than the following approximation. Now I'm approximating 1/3 with 1/4. 1/4 is smaller than 1/3, so that's okay. And then I look at 1/5 and I say, well, that's bigger than 1/8. 1/6 is bigger than 1/8. 1/7 is bigger than 1/8. So that infinite sum is bigger than what I'm now showing down below. But what's down below? I have 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2. I just keep halving, don't I? I just keep adding 1/2s. And what's that going to do? Is that well behaved? No. So this one actually diverges. That one goes off to infinity, even though each of these terms, if you look at the limit, 1/n is getting small, but it's not getting small fast enough to actually converge. So I just want you to be comfortable with these examples in very basic terms so that you understand when you can talk about this geometric series and why it makes sense to say, oh, this is a common ratio, and we can use that to determine whether this converges and what our region of convergence is. In this case, for the harmonic series, that diverges, and we can't look at a closed form solution for that. For the geometric series earlier, we could collapse that whole string of infinite sum down into just a single number, a closed form of 2. Now, what we want to do is extend that to something that looks more like the Z-transform. The 1/2 was very clean, but now we want to make it a function of Z. Let's now look at what happens when we look at this unit step that we talked about last time. But for the geometric series, I hope it's clear that this common ratio, when it has a magnitude less than 1, then that infinite sum will converge and you can find a closed form expression. That's what I want you to take from this little background discussion, one of the things. In our case, if we look at the unit step in the discrete time setting, we have our, by definition, the Ztransform of that unit step. You could say, oh, it's this two-sided infinite sum, but we know little u of n, that the waveform is 0 over the negative indices. We can change our index to n equals 0 to infinity. We can then replace u of n with 1, and now we're just summing all of these z's raised to minus n powers, where n goes from 0 to infinity. In this case, we have 1 plus z to the minus 1 plus z to the minus 2 plus z to the minus 3. Now we have this expression, but I hope you can see that it has the same kind of structure as before, except now, what's the common ratio? What happens each time we add on a new term? What's the factor between the next piece in that sum and the previous piece in that sum? What's the factor? It's not a very restful sleep. It's just 1z, isn't it? But it's downstairs. It's 1 over z. It's z to the minus 1. So if you're playing along at home, you can go get your pillow. In class we did. We all laid our head down and we just had a 1 time step nap, right? A 1 over z, or a z to the minus 1. We just had 1z, not a bunch, but we will get a bunch when we string them together. But the common ratio is now z to the minus 1. Is that clear? That's how we get each new term in that geometric series. And what do we want to have happen then for this particular Z-transform to converge, to actually have a finite limit? What do we need to happen? What needs to be less than 1? Like R needed to be less than 1, now what do we need to be less than 1? Our common ratio, that's what R was. In this case, our common ratio is z to the minus 1. We need the absolute value, we need the magnitude of z to the minus 1 to be less than 1 for this particular infinite sum to be bounded, to be well behaved, to be nice. I may say that many different ways. And now I have all these vertical bars. I have to get behind the bars. That's not a comfortable place to be, but never mind. Hopefully you've never experienced that and never will. So what's in the first set of vertical bars? This is an absolute value. We need z to the minus 1 to be less, or which is equal to 1 over z to be less than 1. And now we can multiply both sides by the absolute value of z and see that 1 is going to be, in this case, it's the 1 in the numerator. It's this 1 is now going to be the lower bound on the magnitude of z. I've just multiplied both sides in this 1 over z absolute value less than 1 by the absolute value of z, and I now have this absolute value of z being bigger than 1 allows that series to converge, which gives us a region in the complex z-plane where the sum converges, and we will just refer to that as the region of convergence. The region of convergence now is this unbounded region starting at z equal 1, and z equal 1 is a unit circle in the z-plane. Now our region of convergence is outside of that unit circle. We have a region of convergence, or an ROC, we can now sketch for this unit step. And I didn't want you to make fun of me today, so I pre-sketched that unit circle. Maybe it's a little better than what I might do on the fly, but maybe not. Don't get too critical with my unit circles. But that's supposed to be a radius of 1, and what I've now shaded is the region of convergence. And that's where this particular waveform, the unit step, has a Z-transform. The region of convergence is outside this unit circle. And where were our poles and zeros for this particular closed form expression? Or what was this closed form expression? Do you remember? 1 over 1 minus the common ratio, or Z over Z minus 1. That's what you want to, that's how you want to write it in order to find poles and zeros. Now, our poles and zeros, we had a 0 here and a pole there. And the region of convergence is outside that pole. Our poles will never live or lie in our region of convergence. We're going to have different shapes for the region of convergence. This one is actually for a right-sided or a time domain waveform that was defined for n that was 0, up 1, 2, or non-negative. And that gave rise to this infinitely large region of convergence. But we will find we have different region of convergences with different waveforms, time domain waveforms, defined over different indices. And we'll get there in a little bit. But now this is enough for our region of convergence. Questions on this unit step? We went through it last time rather quickly, so I wanted you to be comfortable with where this region of convergence is coming from and why we were able to find this closed form solution for this infinite sum of z's. We had 1 plus z to the minus 1 plus z to the minus 2, etc. We needed to find the common ratio. Once we had that, we could do this summation trick. Remember, we just copied down the one line, and then we copied it down again underneath and multiplied it by the common ratio, and then we could take the difference, and that allowed us to find this expression for that sum. We'll be doing that quite frequently in this class, or that approach. Let's now step it up a little bit and look at the exponential waveform, which you should be comfortable with in the continuous time case. In the continuous time case, we have e to the at, where a, if it's positive, then we have a growing exponential. That's indicated in the red curve. If a is negative, then we have a decaying exponential. And that's indicated by the blue curve. Just so you don't get confused and expect to have multiple poles when you have a first-order system, I've just indicated one pole for one of the cases. The case where you have an unstable or an unbounded response, the pole now is positive, or it's in the right half S-plane, and that leads to an unstable or an unbounded response for that particular transform. What's going to happen for the digital case? Now, if you are still with your head on the pillow, you can wake up and we can start talking together or taking notes together. Maybe I was going fast before, but you have access to these notes, and I'm hoping a lot of that was simply a review. Let's now look at the exponential, which I think maybe is waveform C. That's now, one way to write that would be r to the n, where n is greater than or equal to 0. Do you see where that comes from or not? Did we do that last time? What if I looked at an analog waveform, x of t is equal to e to the at? And if I sample that, which means now replace t with little n capital T, where t is my sample period, I now have e to the a n t, or e to the ant. Now we have bugs crawling around. We have ants. Just one way to maybe allow you to remember what this exponential looks like. But we can factor that by remembering how to manipulate exponents. We can say that that's e to the at raised to the n, and now this inside parentheses is just our r. So that's one way. We wouldn't have had to obtain that from a sampled time domain, continuous time domain system. We could have just said it's r to the n. But that's one way to see maybe where that r to the n is coming from to produce an exponential. If capital R is bigger than 1, what's going to happen to that exponential? If R is real but bigger than 1, what's going to happen? It's going to go unbounded, isn't it? We have, let's say, 2. 2 squared, 2 to the 2 cubed, 2 to the 4th, 2 to the 5th. That just keeps growing. If R is less than 1, then it's going to be this decaying exponential. And do you see that what R is going to depend on little a and capital T. If a is positive, then it's going to go unbounded. If a is negative, it's going to be bounded. But what capital R is going to be influenced by capital T, how fast you sample. All right, so now we have this digital waveform, capital R to the n, for r greater than or equal to 0, and I hope you can now see that that has different possibilities in terms of its behavior. If r is less than 1, and this is x sub c of n, we will have this behavior, this exponential decay. If r exceeds 1, capital R, in magnitude, then we have this, that's supposed to be a growing exponential. Maybe I didn't draw it very carefully, but it's now going to be a factor of r different at each sample period. Start at r squared, r cubed, etc. What's the pole zero diagram of this going to look like? Can you guess? We haven't really shown it, have we? But what we want to be able to do is talk about where are the poles and where are the zeros for this discrete time waveform. What's its frequency domain pole and zero diagram look like? We want to figure that out. And to find that, let's now take the Z-transform of that exponential. Now you're looking for points in a week from Wednesday. So what's the definition of the Z-transform lead to? How could you simply write down the definition of capital X sub c of z? What would that look like for this waveform little x sub c of z? hopefully you can write that capital sigma at least to give yourself partial credit, very partial credit, but partial. It was defined for non-negative values of n. We'll then sum from n equals 0 to infinity. We have the time domain waveform, x sub little c or little x sub c of n. And now that gets weighted by this complex exponential, z to the minus n, where little x sub n of little x sub c of n is r to the n for n greater than or equal to 0. That's the definition of the Z-transform. And now we need to put in the particular values for little x sub c of n, or the time domain waveform. At n equals 0, we have little x sub c of 0 plus x sub c of 1, z to the minus 1, plus x sub c of 2, z to the minus 2, etc. That maybe isn't very illuminating to look at x sub c, but we can plug in its more detailed expression by using r to the n. R to the 0 is 1. R to the 1 is r, z to the minus 1, plus r squared, z to the minus 2, plus r cubed, z to the minus 3, etc. We're just trying to find a pattern. Or we're really trying to find a common ratio between each of these terms. We could rewrite that. We could say that's 1 plus rz to the minus 1 plus rz to the minus 1 squared plus rz to the minus 1 cubed plus, and now it's starting to maybe be a little bit more clear what that common ratio is between terms. When is this infinite sum going to converge? When will it be well behaved? We need the common ratio to have a magnitude less than 1. The common ratio in this case, is rz to the minus 1, and we need that to be less than 1. That common ratio now between terms in this infinite sum needs to have a magnitude less than 1. And if we now evaluate that for z, that will tell us what our region of convergence looks like. But let's not do that just yet. Let's just assume now that rz to the minus 1 is less than 1 so that we can talk about this sum converging. If it converges, now we can say, oh, capital X sub c of z is now 1 plus rz to the minus 1 plus rz to the minus 1 squared plus rz to the minus 1 cubed, etc. And now you know what I'm going to do. I'm going to write that down, except now multiply both sides by the common ratio. Or I now can say, oh, rz to the minus 1 times x sub c of z produces rz to the minus 1, which is rz to the minus 1 times 1, plus rz to the minus 1 squared, rz to the minus 1 cubed, and the tails are exactly the same. This is an infinite sum, so the tails are the same. We can compare these two expressions. By that I mean subtract the bottom one from the top one, and we end up with 1 minus rz to the minus 1 times x of z is equal to what? It's just equal to 1. And now we can solve that for this Z-transform quantity, capital X sub c of z. This is now equal to 1 over 1 minus r z to the minus 1. And if we want to write that or express that in terms of positive exponents of z, we could factor out the z to the minus 1 and put it upstairs, or we could multiply it by 1, which is z over z. But this now becomes z over 1 z minus r. Is that what the hand was raised for? To correct my typo? It's 1 minus rz to the minus 1 in the denominator. And now our poles and zeros should be screaming at us. And what's our region of convergence? When is this sum, or when was that infinite sum well defined or well behaved? When did it converge? Under what condition? That was this piece, wasn't it? We need the magnitude of rz to the minus 1 to be less than 1, or this expression, this closed form expression, is going to be true when rz to the minus 1 is less than 1, or r over z absolute value is less than 1, or the magnitude of z is bigger than the magnitude of r. And what does that look like as in the complex z-plane? What does the magnitude of z being bigger than the magnitude of r look like as a picture in the complex z-plane? The magnitude of r is just a distance away from the origin, isn't it? And now we're saying the region of convergence for that exponential, either decay or unbounded exponential growth, has a region of convergence such that it's bigger than z. I'm sorry, it's bigger than r. I'm still on my pillow with my z's. So you guys need to keep me awake. Where were we? Where are our poles and zeros? Do we have any finite zeros in this z-transform of an exponential? Where is it? At the origin. This is my z-plane. Where's my pole? Let's just assume that r was positive and that it was real. Where would we draw the pole? Where the denominator vanishes. The value of z that causes the denominator to vanish, or at a value of z equal to r, when z minus r is equal to 0. We then have a pole here at r. And what's the region of convergence? Now I have to try to draw a circle of radius r, so bear with me. But if I tilt my tablet, T and T, tilt the tablet, oh, triple T, isn't it? Tilt the tablet. Doesn't take much to entertain me, does it? I'm glad you tolerate it. Well, maybe you're not tolerating it. Okay, so it's an egg, but it's supposed to be a circle. You don't even want to know what grade I made in art class. Well, I'm sure you do now, but anyway, let's not go back that far. Our region of convergence is outside this pole located at r. Is that clear? That's the region of convergence. And what do we know? We know that this shape for the region of convergence doesn't matter what r is, whether it's less than 1 or bigger than 1, the region of convergence is beyond it. So whether this system actually, or this signal, would be stable or not is a different question. The region of convergence is still beyond R. Let me just write that down. The ROC, the region of convergence, is outside R, or beyond R. I don't know how you like to interpret my English. Maybe my English wording isn't the best. But the region of convergence is outside R whether the magnitude of R is less than 1 or the magnitude of R is bigger than 1. It didn't matter what R was. Our region of convergence is such that it forces that R z to the minus 1 to be less than 1. So z is going to be beyond or larger than R. Question? So the question is, does the region of convergence mean that it's stable? So you have to divorce these two concepts. The region of convergence is only concerned with when this infinite sum is bounded. That's different than whether the waveform has a exponentially damped or an exponentially growing. We can have a Ztransform for an exponentially unbounded waveform. Its region of convergence will just be beyond or outside the pole. That R could be at 2, and that's fine. Where's the unit circle? Well, it's inside that R, so we don't have our pole inside the unit circle, do we? But what if R was 1/2? Then our region of convergence would be outside of 1/2, and that unit circle would actually be inside our region of convergence. Ding, ding, ding. But don't worry about that just yet. Okay? Let's just worry about the region of convergence. We'll talk about stability later. But for now, we just need to find what values of z cause this infinite sum to be well behaved, or those terms to eventually become or approach a bounded value. Question? And the region of convergence is bounded by the pole's location. Correct. And the pole is not in the region of convergence. It's just right up against it. Okay? But it's not in the region of convergence. The region of convergence is beyond that pole, even though my picture shows it, but it's right on the boundary of the region of convergence. Any other questions? All right, that means it's time to move on. We've looked at constants. We've looked at exponentials. I'm just enjoying doing my exponential dance. I'm sorry for those of you that don't get to see that, but you can stand up and do your own dance. When I say the exponential dance, that means that you're going, okay, let's just stop dancing. Now what do we want to talk about? Now we want to talk about sinusoids. Now you can just sit and rock in your chair with a sinusoidal pattern. But what we're going to do is we're going to damp those sinusoids so that they don't keep going and going. Okay? What about exponentially damped sinusoids? In our learning process, it always helps to go back to what we remember, or what we're supposed to remember. Okay? So let's look at what this looks like in the continuous time case. Let's say now we have an exponentially damped sinusoid, which I'll just play with a cosine. I like that because it starts at 1 when t is equal to 0, or its argument is 0. If I don't have a phase shift, and I'm not going to put a phase shift in I'm artistically challenged, so you know that I'm going to try to do it as easily as possible. Here's our exponential damped piece, e to the minus sigma t, and here is our sinusoid, omega sub dt. And we want to look at this for a right-sided transform or a one-sided waveform. Do you remember now what the Laplace transform of x of t looks like? And that's a double-headed arrow, meaning if I give you capital X of s, you should go back to little x of t, or if I give you little x of t, you should be able to find capital X of s, or write it down. Does anybody remember what that is, or are you brave enough to volunteer an expression? Okay, where are your poles? And I should, for some of you, this should just be screaming at you because of the parameterization of the exponentially damped sinusoid, a sigma and an omega sub d. Hint, hint. I don't know if everyone heard that, but I just heard the correct answer. Does that look familiar? That's our denominator. It's s plus the real part squared plus the imaginary part squared. That's our denominator of this Laplace transform. Maybe to emphasize this, I'll do it that way. And for the cosine, we do have an s in the numerator, and it's s plus sigma. If you remember the Laplace transform of a cosine, then the sigma is 0, and we have s over s squared plus omega sub d squared. That's the Laplace transform of a pure cosine. When it's damped, we introduce this s plus sigma piece, or replace s with s plus sigma. And now in the s-plane, what do we see for our pole zero diagram? I'm now into the left half plane, a value of minus sigma. Where's my 0? What value of s causes that capital X of s's numerator to vanish? Is there such a value? What time is it anyway? Are we awake or are we zing still? Hopefully it's there, right? And where are our poles? It's parameterized such that the real part is minus sigma and the imaginary part is j omega sub d. Our poles are complex conjugates. Ooh, that's supposed to be the same distance positive as the same distance negative. Again, if it's not, you can make yours more accurate. This is the pole zero diagram for the continuous time, or the analog waveform in the S-plane. We want to know, one, what's the Z-transform look like for a discrete time exponentially damped sinusoid? What does it look like in the time domain, and what's its pole zero diagram look like? That's where we want to go. Or if you don't want to go there, that's where I'm taking you, just as the audience is tough tonight. Discrete time. Let's just start with the continuous time. That was e to the minus sigma t cosine omega sub dt. And now we just go back to our friend. You guys have a lot of friends. One of them is Euler. Remember Euler? All right, maybe he was not in your generation, but I had a good friendship with Euler. So here is e to the minus sigma t, and how can we parameterize cosine in terms of complex exponentials? And it will become clear why we want to write this cosine in terms of complex exponentials. Because we like to play with exponentials, actually. Or this now, this x of t, we could factor out the 1/2, and I could now say e to the minus sigma t, e to the j, omega sub dt, plus e to the minus sigma t, e to the minus j, omega sub dt. Or this is now e. I can add algebraically those exponents, and I now have minus sigma plus j omega sub d times t plus e to the minus sigma minus j omega sub dt. And it might be easier to just think of this as a point s sub 1 in the complex s plane, and this as its conjugate. Call it s sub 2. This now will be a convenient way to write a exponentially damped cosine. Now we have just exponents, or these e's, with a t in the exponent, because now we want to sample that continuous time waveform. Suppose we sample or another way of saying that, or we find a discrete time representation or expression. So that now I'm looking at x of t with little t replaced with little n capital T, and I now can have 1/2 e to the minus sigma plus j omega sub d little n capital T plus e to the minus sigma minus j omega sub d little n capital T. And now I can simply play or go backwards with some algebra. Let me now pull those exponents apart, put them into two pieces, so that I can now see a common piece of e to the minus sigma nt, and you've seen that earlier tonight. That was this r piece, or r to the n piece. I can now say that this is 1/2 e to the minus sigma nt, e to the j omega sub d nt, plus e to the minus sigma nt, e to the minus j omega sub d nt. Let me factor out a common piece from those two terms, and that common piece now is going to be e to the minus sigma nt. What's left inside the brackets will be e to the j omega sub dt raised to the n plus e to the minus j omega sub d t to the n. To make this maybe a little bit cleaner, maybe I just call that omega sub d capital T an angle theta, theta sub d. Or what do I have in square brackets? I now have e to the j theta sub d n plus e to the minus j theta sub d n. And that should remind us of our friend. Maybe. Euler. Right? No? He's on Facebook. You should have already been friends with this guy. So now this is Euler screaming at us, or we now have 1/2 e to the minus sigma nt, and e to the jx plus e to the minus jx is 2 cosine x. So we now have 2 cosine of theta sub d n. Those 2's, let's just clean those up, get rid of them. They cancel each other out. And now what do we have? We now have e to the minus sigma n, or maybe I should pull out that n. Let me say we have e to the minus sigma t to the n times cosine of omega sub dt. Now I'm putting that parameterized form of theta back in there, and now you can explicitly see what we started with. We started with sigma and omega sub d, and now they've magically reappeared in our discrete time exponentially damped sinusoid. This is x of n t, and a lot of times we'll just suppress the capital T. But this is our r, and this is our theta sub d. And if we wanted it, then we have x of nt is r to the n cosine theta sub d n. And there is now a exponentially damped sinusoid for a discrete time system. As a function of n, we could now evaluate that, and what would we see? We would have some exponential damping if r is what in magnitude? What am I assuming by having damping? R is less than 1, or sigma or minus sigma was in the left half plane, and we also have a cosine waveform that's being collapsed by, but that's supposed to be a cosine waveform, and it now is occurring at a particular instance of time. Depending on how quickly or how fine we sample that waveform. And don't hold me to having the same number of samples in each half cycle of this sinusoid. Again, my artistic ability is challenged. But this piece is our e to the minus sigma t if it was in continuous time. Now it's this r to the n shape that collapses this sinusoidal, this cosine waveform as a function of t. We want to now Z-transform that. We want to find the Z-transform. It's not exponential, it's not sinusoidal, it's a combination. It's an exponentially damped sine wave that's in discrete time. And here I won't just call it a sinusoid, I'll just say the cosine, because I do want to specifically use the cosine waveform. Your homework will be a sine. Hint, hint. Maybe you've already completed that assignment. That's homework number 2. Little x of n is now 1/2 r to the n e to the j theta sub dn plus e to the minus j theta sub dn. And it's one-sided, meaning we now have this expression for n greater than or equal to 0. And you should be comfortable with that. That square bracketed piece is a cosine waveform with an argument of theta sub d in. Let's now plug this time domain waveform into our Ztransform expression or formula, which says now that to find the Ztransform, we need capital X of Z is going to be this infinite sum, a one-sided infinite sum because it's 0 for negative values of n. Little x of n is 1/2 r to the n e to the j theta sub d plus e to the minus j theta sub d z to the minus n. In curly brackets, that's just little x of n. And that's a exponentially damped, if r is less than 1, cosine. Question. Is there a reason I dropped the n from the square brackets? No, I've just got my head on my pillow. Thank you. So the n should be scaling theta sub d in the exponent inside the square brackets. Thank you. Just making sure you guys are awake. Only one of you caught it. 1% is our settling time. 1% capture rate. Never mind. Question. So the question was, when do we and when don't we include the sampling period, capital T? It really depends. Somebody might just give you this expression right here and say, here is the discrete time domain waveform. And they may not explicitly identify a sampling period, capital T. They may just give you an R, raise it to the n, and an angle theta sub d, and that's now your argument of the cosine. If it's actually coming from a sampled waveform, then you know embedded inside R is a sample period, capital T. R is e to the minus sigma, capital T. And if you knew sigma and capital T, you could compute R. It just depends on what you're given or what you're working with. But typically now, we will simply, where did it go? It's embedded in R if it's there, and it's embedded in theta sub d. Theta sub d is omega sub d capital T, where omega sub d was our damped oscillation frequency in the continuous time waveform. So it may be important, it may not be. It just depends on the context, whether we need to worry about the sampling period or not. Does that help? But now what I want to do is not worry about capital T and just play with this expression for little x of n and see what falls out. Meaning, I can now, this looks a little bit messy, let me break it or separate it into two sums using that plus sign inside the inner square bracket. Or I can now say that this is equal to one sum from n equals 0 to infinity of, that 1/2 doesn't need to be inside this summation argument. I do need to keep everything that's a function of n inside the summation. Now I have r to the n, e to the j, theta sub d n, z to the minus n, plus another infinite sum, 1/2 can be factored out of it, n equals 0 to infinity, r to the n, e to the minus j, theta sub d n, z to the minus n. And I can just keep going. I have an n in common in the exponent of all three of those pieces in the argument of my infinite sum. Or I now have r e to the j theta sub d z to the minus 1 to the n. And I think you can see where I'm going with this. I'm trying to find a common ratio. And I have a plus 1/2 summation from n equals 0 to infinity of r e to the minus j theta sub d z to the minus 1 n. And now you can maybe see why I separated that into two sums, because the common ratio is different between the two. If you're getting tired like I am, maybe we want to just relabel things. Let me call that mess in the first sum x sub 1 and the mess in the other one x sub 2. So that I now have x1 to the n and x sub 2 to the n in the respective sums. Or I can now rewrite this and say that capital X of z is now 1/2 summation from n equals 0 to infinity x1 to the n plus 1/2 summation n equals 0 to infinity x sub 2 to the n. And now we are instantly aware of what that becomes, right? We know it's closed form expression. What's the common ratio in the first summation? x1. Let's just write it in terms of those x's. And the common ratio in the second sum, x sub 2, so that we can now collapse this down to 1/2, 1 over 1 minus that common ratio, plus 1/2, 1 over 1 minus x sub 2. Here we're making an assumption, obviously. We're assuming that rz to the minus 1, essentially, is less than 1. That e to the j theta sub d has a magnitude of 1, doesn't it? In all of those cases. And you can find that by going back to Euler's Facebook page and looking at Euler's equation. E to the j theta is cosine theta plus j sine theta, and what's the magnitude of that complex number? Cosine squared plus sine squared, and that equals 1. And I'm not going to tell the joke again about, never mind. Okay, with this, not the joke, but with this. Inside joke, maybe. But we can now clean this up. What is capital X of z? We can combine these two pieces. Get a common denominator, 1 minus x1 and 1 minus x sub 2. And what do we have? Well, over here we have 1/2 1 minus x sub 2. And here we have 1/2 1 minus x sub 1. And if we divided that up, we should end up with the equation above. Let's clean up the numerator and denominator in terms of these x's. And now you know why I'm picking with x's or sticking with x's. It has more internal expression collapsed down in these x's. But for now, capital X of z, I have 1/2 plus 1/2. I can even do the math at this time of evening. 1. Right? 1/2 plus 1/2 in the numerator. And then what do I have? I have the sum of x1 and x2 scaled by a minus 1/2. What's downstairs? I have this product of two terms. I have 1 minus x1 plus x sub 2 plus x1, x2. Algebra. What do I have? Well, I need to know what is x1 and x2, since that's occurring in my denominator. That was x1 was r e to the j theta sub d z to the minus 1. X sub 2 was r e to the j theta sub d with a minus z to the minus 1. That was x1. That was x sub 2. What happens when I multiply those two together? I have an e to the j x times an e to the minus jx. I'm really just putting all of those exponents together. I have r squared, e to the j theta d minus j theta d. E to the 0 for that piece. That's 1. So it goes away. And I have z to the minus 1 times z to the minus 1. This piece now becomes r squared z to the minus 2. Whenever I see an x1 times an x2, I can replace it with its real expression, r squared z to the minus 2. What about x1 plus x sub 2? That's r e to the j theta sub d z to the minus 1 plus r e to the j minus j theta sub d z to the minus 1. Let me factor out a common term from both of those. And I now have e to the j theta sub d plus e to the minus j theta sub d. And if you have your Facebook open, you know what that is. We're back on Euler's homepage, or Facebook page, right? Go home tonight and friend Euler. He'll feel that much better. What do we have? We have r z to the minus 1, 2 cosine theta sub d. Or x1 plus x sub 2, when we see that in our expression, is 2r z to the minus 1 cosine of theta sub d. What's capital X of z then? We had it in terms of x's summed and product. Now just replace what we know. We have 1/2 times the sum, and there was a 2 in that. That goes away. Or upstairs we now have 1 minus r z to the minus 1 cosine theta sub d. There's our numerator of our, what are we doing? We're Z-transforming a complex exponential. I'm sorry, an exponentially damped cosine waveform. What's the denominator? That's now 1 minus the sum of x1 plus x2, which is 2r z to the minus 1 cosine of theta sub d, plus x1, x2. x1, x2's product was r squared z to the minus 2. Maybe we don't like to see that in terms of negative exponents on z. How can we clean it up? What's the highest power of z in the negative sense? 2, z to the minus 2. So if we multiply by 1, which is z squared over z squared, we end up with z times z minus r cosine of theta sub d, and I hope you can see where the zeros are. And downstairs we have z squared minus 2r cosine of theta sub d z plus r squared. Which means if you now have an exponentially damped cosine in the time domain, which is maybe parameterized by an r and a theta sub d, boom, you can just write this down. You don't have to rederive it. Hopefully you believe it. And this is now the Z-transform. Can you find the poles and zeros? The zeros are easy, aren't they? We have one at the origin, and we have another one at r cosine of theta sub d. And then we need to find out where the poles are. I'll let you do that tonight while you're sleeping, right, with your z's. Well, don't forget you have a homework assignment due by this evening for homework number 1. Enjoy your evening.